for the polynomial parts of the final, for those who weren't here, the question is something you would have seen, but just the numbers are changed. Okay, so do not worry too much about it. Well, I mean, worry about it, but it's not something out of the ordinary. And you know, this type of questions, yeah. So it's something you would have seen, but the numbers change. Again, I planned that we're gonna be a bit short on time. Well, not short on time, but you know, the last two lectures I'm not gonna introduce examinable material, so I will just be nice calculations. In my opinion, they shouldn't take too long. You know, 1 minute and 1 minute. The exercise could take you 2 minutes, maybe, if you know what you're doing. Okay. So yeah. Okay, great. Well, not 2 minutes. Let's say 1 minute per. Let's say 3 minutes. 3 minutes. You could be done with the exercise on the final if you know what you're doing. Okay. But I will post some practice questions, and I'll post a practice final. Okay. So I encourage you to look at them. Okay. The practice final will be posted next Wednesday, and practice question I posted one set already, and the next set will be posted, I don't know, maybe during the weekend. Okay, and then we can go over it on Tuesday. Okay, yesterday we had a nice review session. Very good questions were asked, so please I invite you to look at the recordings. Not too many were attending, but please, very, very good questions were asked, and we did a lot of questions. So, yeah, please I invite you to have a look. Okay. Where do I have? Okay, so last time we introduced the Euclidean algorithm for polynomials and the GCD of two polynomials with coefficients in a field F. Okay? Now, so proposition or definition. Here, let F is a field. F of X, the ring of polynomials with coefficients in F. Okay, definition. Let F of X be a, let's say, non-constant, well, be a polynomial in F of X. We say that alpha in F is a root of F of X if F of alpha is equal to 0. Okay, so I will drop the 0 F. I'll just say 0. Yes, sir. Yes. Yes, that's a lot of words or what's more called here. Sure. Okay. So proposition. Let F of X be F of X. Alpha is a root of F of X if and only if X minus alpha divides F of X. Okay, let's prove this. The proof is quick. Proof. Which one do you want to do first? Let's do this way. Suppose alpha is a root. What does alpha as a root mean of F of X? Means that, yeah, okay, did I say alpha belong to F? Alpha belongs to F here. In F of X. Okay, so suppose that alpha is a root of F of X, then what can I say about alpha? Then F of alpha is 0. Now, of course, if F is 0, then the result is obvious, right? I mean, you know, suppose that F is not the 0 polynomial, or we can put it as 0, that doesn't matter. Okay. Okay? So if r of x is 0 or r of x is a constant, basically, non-zero constant. So basically, so f of x is equal to x minus alpha. This is the Euclidean division. G of x plus k, that's plus r, where r is in f. Now plug in alpha on both sides. Plug in alpha. This means that f of alpha is equal to alpha minus alpha times q of x plus r. Well, f of alpha is 0 because alpha is a root. Alpha minus alpha is 0. So r is 0. Okay? It's r is 0. And so f of x is q minus alpha times q of x. So x minus alpha divides f of x and f of x. Great. Now let's do the converse. The converse is like that. Can I erase here to keep the proposition? Can I erase here? Yeah. Can I erase here? Yeah. Now let's do the converse, which is more or less obvious. Suppose that x minus alpha divides f of x, then f of x is equal to x minus alpha g of x for some g of x in f of x. Now plug in alpha on both sides. F of alpha is alpha minus alpha times g of alpha, which is 0. So alpha is a root of f of x. Okay, great. So,
Yo, bro, that was way too fast.
Kirby? Yeah.
I'm not sure to understand why r of x is specifically 0.
R of x has degree 1 or 0. Has degree 0 or is a constant, right? R is a constant. R of x is a constant. Agree?
Why?
Because it has degree less than 1.
Why does it have degree less than 1?
Because you're dividing f of x by x minus alpha.
Which has degree 1?
X minus alpha has degree 1.
Yeah.
So R of x must have degree less than 1. Exactly. Okay? Great. Okay, now we'll define a very important notion, the notion of an irreducible polynomial.
Oh, God.
Is there anything?
It goes quickly.
Yeah, that's way too quick.
It's like
It's way too quick. That's okay.
Wait,
Yeah, can I take a picture of these?
Oh, it's too quickly to erase?
Yeah.
Oh, okay. There's a recording. It's a recording. Okay.
Sir, that's not.
Hey, there is a recording. I'm sorry.
This goes.
Which one?
What is light speeding?
Okay. Great. Now let's see. This is why I don't like to have notes with me. You know, if I have notes with me, I'll just go through both. But anyways. So a non-constant definition. A non-constant polynomial f of x in f of x is said to be irreducible in f of x if, I don't know what definition I gave, there are many definitions. Yeah, if f of x cannot be expressed as a product of two polynomials what do I say? G8 strictly smaller degree. Are we good now? I can erase. Okay. In other words, if f of x is irreducible, it means you can't factor it. Okay, you have seen polynomials that you can't factor anymore, right? You have seen these things before, no? So if you take a quadratic over r, which has no roots, can you factor it in r? You take the delta is equal to b squared minus 4ac, right? That's what you do, right? If the delta is negative, you cannot factor it in r. That's an irreducible polynomial in r of x, right? Yeah? You have seen this before? We have seen delta equal b squared minus 4ac, and then you take minus b plus or minus root delta over 2a, and then if the delta is negative, you don't have real, yeah, you have seen this, right? I hope so. Okay? So in other words, if f of x is irreducible in f of x and f of x is g of x h of x, then g of x is a unit, so basically is a non-zero constant, or h of x is a unit. Okay? Basically, an irreducible polynomial is a polynomial that you can't further factor. It's just like a prime number. Can you further factor a prime number? No. An irreducible polynomial is a polynomial that you can't further factor. So if you have a prime number, say p is equal to a times b, what can you say about a in z? What can you say about a? Yes, say something. P, yeah?
One of them is 1.
One of the, okay, so let's allow negatives here. So one of them is 1. So you want to say a is 1 or b is 1. But let's say that a is minus 1 or b is minus 1. If we want to extend it to integers, right? And 1 and minus 1 are the units in z. These are the invertible elements. Same thing over here. An irreducible polynomial is a polynomial that you can further factor. If you were to write it as a product of two polynomials, then one of the polynomials is a non-zero constant. That's it. No more, no less. It plays the same role as prime numbers in f of x. So all the things that will hold for z, we will have an analog in f of x, and the proofs will just be the same. The proof will just be the same. Okay. I mean, this is the definition of a prime number, right? If p is equal to ab, then a is plus or minus 1, right? The only divisor of a prime number are plus or minus 1 or plus or minus p. Yeah?
No, I think we're good.
You're good? Thanks. Okay. Okay, let's give an example. Let me see if I should have that. Okay, let a be non-zero. Well, let a be non-zero. Then f of x is equal to ax plus b is irreducible in f of x. That's obvious, right? Try to write something of degree 1 as a product of two polynomials. What can you say about the degrees of this? If f of x is g of x times h of x for some gh in f of x, what can you say about the degree of g and the degree of h? So you know that the degree of f is equal to the degree of g plus the degree of h, since f is an integral domain, right? From last time, we proved this, right? Since f is a field. So an integral domain. So what is the degree of f here? The degree of f ax plus b. What's the degree of ax plus b if a is non-zero? Everyone? Degree of ax plus b?
0 or 1.
The degree of ax plus b is what? 1, right? A is non-zero, so the degree of ax plus b is 1. So 1 is the degree of g plus the degree of h. What can you say then? One of them must have degree 0, right? So degree of g is equal to 0, or degree of h is equal to 0. So f is irreducible. Yeah?
Can it be like the degree of g is equal to 1/2?
No, these are not polynomials anymore. We define polynomials as positive, non-negative integer powers. Okay, of x. Okay? So degree of g is equal to 0, or degree of h is equal to 0. So g is a unit, so g of x is a unit, or h of x is a unit. So f of x is irreducible. Okay, let's give another example. Let's give another example. Let f of x b and f of x have degree 2. Then f of x is irreducible in f of x if and only if what? F of x has no roots. This is also not very bad to see, right? We can see this. Can you see this?
We can just use the contrapositive of the thing we
Yeah.
did before. And that
Yeah.
works.
Exactly. Are we good? Are we following, or it's a bit fast?
No, it makes sense.
Are we following?
Yes.
Yeah. So let's do it. Which way do you want to go first? Let's go like that first. So suppose f of x is irreducible. I mean, this holds true for any polynomial greater or equal to 2. Is irreducible. Since the degree of f of x since the degree of f of x is bigger or equal to 2, then x minus alpha does not divide f of x, right? Yeah. Agree with this or not? If f of x is irreducible, then you cannot write it as a product of two polynomials of smaller degree. Agree or not? Then x minus alpha cannot divide it, because if x minus alpha divided it, you would be able to write it as x minus alpha times something else. And this contradicts the irreducibility. And hence f of alpha, and hence, oh man, then for any alpha should be correct. And for any, or you know what? Let's do it the other way. Sorry, I mean it's better the other way. So suppose, yeah, f of x has a root alpha, then f of x is divisible. I mean it's the same thing, but by x minus alpha, and so, and hence f of x is x minus alpha times q of x for some q, and f of x, and so f is not irreducible. because this is not a unit, right? And q of x is not a unit because their degree should be linear. Q should have degree 1 if you think about it, right? F has degree 2, x minus alpha has degree 1, so this must have degree 1 in that case. Okay, now let's do the other way. The other way is more interesting. So what do I say? So if, suppose now f of x has no roots. Has no roots in f. How do I show that f is irreducible? So you have a degree 2 polynomial and it has no roots. How do you show you cannot factor it? Yeah?
But you can't factor it since you can't write like x minus alpha.
Exactly.
X just doesn't exist.
Okay, that's good. But does it work for higher degree polynomial? If you have something of degree 4. So take x squared, so let's work with real numbers. So let's work with x squared plus 1 squared. Can you factor x squared plus 1 squared over the real numbers? You could. It's x squared plus 1 times x squared plus 1. But does it have a root? No. But here, you want to say that if you can factor it, what it means that you have a root. Is that what you meant to say?
No, if you can factor it with like units, like a unit time.
Yeah, but if you...
Oh, but you can like plainly factor it between polynomials.
No, I mean, is that what you meant to say? That if you factor the degree 2 polynomial, then one of the factor must have a root. I see, okay. Yeah. So suppose f of x has no roots in f of x, and let h of x, g of x in f be such that f of x. What are the possible degrees of h and g? Degree of f is 2. So what can I say about the degree of f and g?
One of them is the degree of f.
Dig g is equal to degree of h is equal to 1, or degree of g is equal to 0 and degree of h is equal to 2, or degree of h is equal to 0 and degree of g is equal to 2. Can this hold? Can you have both having degree 1 if f of x has no roots? If you have a polynomial of degree 1, does it have a root over a field? Ax plus b, where a is different than 0. Can you solve for x or not? Ax plus b, you're in a field. Can you solve for x? Can you find a root for this polynomial? X is minus a inverse times b. So can both have degree 1 here? Exactly. In that case it works because 1 plus 1 is 2. Now take a polynomial of degree 4 that is irreducible. Take a polynomial of degree 4. Let's take x squared plus 1 times x squared plus 3 over the reals. By definition, this is not irreducible because I just factored it. Does it have a root? Does it have a root on the real numbers? So this is true for degree 2. It does not necessarily hold true for degree 4 or more. It's also true for degree 3. And I'll leave it to you as an exercise by the same argument. But if degree of g is equal to degree of h is equal to 1, then f of x will have a root. In f. So we must have that degree of g is 0 or degree of g is 2, and hence f of x is irreducible in f of x. So to check that a polynomial of degree 2 cannot be further factored in f of x, or is irreducible in f of x, it is sufficient and enough to show it has no, it's sufficient and enough to show it has no roots. Okay, yeah?
Back to the definition of reducibility, we're assuming that g of x and h of x are non-constant quantities as well.
No, they could be constant. Irreducibility means that one of them must be constant. F of x is irreducible. If in any ways you can write f is equal to gh, then g or h must be constant. Okay? Great. Can I erase here now? Can I erase here? No, here I can't erase.
No.
I need to do an
Where is
erasal
the other
transformation
side?
upstairs.
No, the other side.
Okay? The same proof, the same argument works if you have a degree 3 polynomial. So if you have a degree 3, if f of x has degree 3, then f of x is irreducible in f of x if and only if f has no roots. Now can I erase this now?
Yes.
Yes, now it's good. Prove left as an exercise. And you can do it verbally. Same method works. How do I do that? So if you can factor f, one way is obvious. If f is irreducible, then it clearly has no roots. The other way, suppose that f has no roots, and you write f is g times h. What are the possibilities for the degrees of g and h? You either have 1, 2, right? Because f has degree 3. If it's 1, 2, then it means that f has a root. You cannot have degree 1. That goes away. The only possibility is what? 0, 3. Exactly. Same argument. Is it clear? Is the argument clear? Everybody, is the argument clear? Yes.
Don't degree 3 polynomials always have at least one root?
In real numbers, yes. Not necessarily in other fields. Over the real numbers, yes. Sorry, could you? Okay. Oh yeah. So over real numbers is it's true. Any odd degree polynomial has a root over the reals, yes, but not over any field. Yes.
Does it work for like n greater than 2? Is that the whole problem?
Let's see. So if n is 4, does the same argument work? So suppose f has no roots. Okay? And you write f is g times h. What are the possible combinations? 2 and 2. Exactly. So it doesn't work. It works only for degree 2 and degree 3. Okay? Great. Now it's good. Now we're going to do the most important theorem for you. This is the most important theorem in this section. Here I can erase. No, here. Now it's here. No, where should I erase? Here?
Yes.
Here's good? Okay. Theorem. This is the most important theorem. This is the theorem you're going to use in your final. Okay? I'm being very clear here. You have 1 week. This is the theorem you're going to use in your final. Okay? Let f be a field. And let f of x and r of x and f of x, right, be a non-constant polynomial. Then f of x, the quotient ring, modulo the ideal generated by f of x, is a field if and only if f of x is irreducible in This is the most important theorem. So I'm not going to ask you any proofs from this section, okay? This is why I went a bit fast. I went a lot fast. But you just have to know the results, okay? So this is the main theorem that you have to know. Let's forget about things like that and look at Z. Replace f of x by z. Z modulo nz is a field if and only if what? N is? When is z mod nz a field? Everybody? If and only if? N is? Exactly. And f of x modulo f of x is a field if and only if f of x is irreducible. Do you guys see this? It's the same analog. What's an irreducible polynomial? It's a polynomial that you cannot further factor. What's a prime number in Z? It's a prime that you cannot factor. Same analog. And same proof. Same proof.
It looks so complicated.
It looks complicated because of the f of x, right? Now, in general, you have a more general framework that makes things a bit easier. That's why I don't like this thing here. But you have a general framework that makes things easy. We call this principal ideal domains, or even there are better Euclidean domain. This is a Euclidean domain. You can put a Euclidean division on it, and all the theorems will hold true. Okay. Should we do some examples before I prove it or not? Let's do examples before proving it. I think because in the exam you'll have examples. Okay. Let F2 be the field with two elements. Can you give me an irreducible polynomial of degree 2 in F2 of x? So I want a polynomial of degree 2 that has no roots. Yeah? X squared plus 1. Let's have a look at x squared plus 1. So let f of x is equal to x squared plus 1. Let's plug in 0 here. What do we get? F of 0 is equal to what? What is F2, by the way? F2 is just z mod 2, right? The field with two elements is just z mod 2. Okay? What is f of 0 in that case? Everybody plug in 1. What is f of 1 in that case? This is 1 plus 1, which is 2, which is 0. So is this polynomial irreducible? If you plug in 1 here, you get it's 1 plus 1, which is 0. Okay? If you want to factor it, you can factor it this way. This is x plus 1 squared. But what can you add here to make this one, what can you add here?
X.
You can add x here. Okay? If you add an x here, what is f of 1? F of 1 is 1 plus 1 plus 1, which is 1. So f of x has degree 2. And has no roots in f2 of x. F2 is a field. Has no roots in f2, sorry, in the field f2. And so f of x is irreducible in f2 of x. And so what can I say? F2 of x modulo x squared plus x plus 1 is a field. Okay, now let's think a bit of this field. What are the, if you take z mod pz, for example, what are the elements of z mod pz? It's the possible residue classes when you do the Euclidean division by p. right? And here it's going to be the same thing. These are just the cosets. Representative of these cosets are the possible residues when you divide a polynomial in f2 of x by x squared plus x plus 1. What are these polynomials? These polynomials, how can you represent them? How can you represent them? How can you represent them?
By other functions not representable by x squared plus x.
Sure, but how can you represent them? Write down f of x. So, as an exercise, write down f of x as x squared plus x plus 1 times q of x plus r of x. What can you say about the degree of r in that case? It's strictly less than? Strictly less than? Everybody? The degree of r is strictly less than Euclidean division. Okay, so really what you can represent any class of polynomial by a class of a linear polynomial. So let I be the ideal generated by x squared plus x plus 1. Take the residue class mod I. What do you get here? Take the residue class mod I. What is f of x plus I? The coset of f of x plus I. What is that? Take everything modulo the ideal I. What do you get?
Rx plus I.
Rx plus I. Exactly. Does this one belong to I? Does this thing belong to I?
Yes.
X squared plus x plus 1 times q of x belongs to the ideal generated by x squared plus x plus 1. So this one is 0 modulo I. You remember the congruence modulo I we defined? No? Yeah? This is 0 modulo I, and this is r of x plus I. So f of x is equal plus I is equal to r of x plus I. Or what you can say is that f of x minus r of x is equal to x squared plus x plus 1 times q of x, which belongs to I. Hence, the coset of f of x is equal to the coset of r of x. And any element can be represented uniquely in this form. So if f of x, this r of x is unique, you cannot find two r of x of degree 1 for the same f of x. You cannot find two remainders, right? The remainder is unique. Okay, now let's write down the elements. So really the remainders are in bijection with the linear polynomials. Okay? So, well, not linear, but the degree at least 1. Degree at most 1, sir. What are the polynomials of degree at most 1 in F2? You have the constant 1, you have 0. I'll call this I, so you have 0 plus I. You have 1 plus I. You have x plus I. And you have x plus 1 plus I. These are the elements of f2 of x mod x squared plus x plus 1. Do you want to play with this ring a bit? Should we play with it a bit? Let's take the product of two elements. What do you want to do? Let's take x plus I times x plus 1 plus I. The rules of the game are simple. Whenever you have x squared, what can you replace it with? In this ring, what is x squared equal to? X squared plus x plus 1 plus I is equal to 0 plus I. Do you agree or not? Because this one belongs to I. Right? A plus I, if x belongs to I, this is just cosets. If, yeah. Cosets and subgroups? No? You remember this? If x belongs to H, what is XH in groups? H. Okay, this is a subgroup, I. And this element belongs to I. What is this coset? It's just 0 plus I, which is I. Same logic. Great, now let's do that. What is the product of these two? This is just x times x plus 1 plus I. So this is just x squared plus x plus I. What is x squared plus x plus I? What is x squared plus x plus 1 in that case? So x squared plus x plus 1 is congruent to 0 mod I, if you will. Right? Now x squared plus x is congruent to minus 1 mod I, which is congruent to 1 mod I because you're in ZQ. Ta-da! This is 1 plus I. So nice. It's a field with how many elements? How many elements does this field have? How many elements does this field have? 0, 1, 2, 3, 4. What is the characteristic of this field? Characteristic is? What is the characteristic? The characteristic of a finite field is the additive order of 1. What's the additive order of 1?
It's 2.
1 plus 1, what is that? F2 of x mod x squared plus x plus 1?
It's 2 plus I.
It's 2,
0
right? You see that or not?
Mm.
The additive order of 1. It's 1 plus I plus 1 plus I, right? This is 2 plus I. Agree? The coset 2 plus I. Now what is 2 in F2 of x mod x squared plus x plus 1? 2 is equal to 0. You're working mod 2, right? So this has characteristic 2. So this is the first time you see we proved results on finite fields, right, that they have size p to the n. But this is the first time we construct a finite field of size not a prime, the square of a prime. Yes?
But the identity, is it 0 plus I or 1 plus I?
No. You look at for the characteristic, it's the additive order, if it's finite, it's the additive order of the multiplicative identity. Okay? Are we good here? Should we do one more? Should we do one more example? What time is it? 19? So we have time. Okay, we have time. We have time. Let's look at a field with how many elements you want. So we'll work with degree 2 and degree 3. Someone give me a prime, not too hard, not too... 5. Let's work with 5. Let F construct a field with 25 elements. So all I need to do is find an irreducible polynomial of degree. So 25 is 5 squared, right? Agree or not? So I need to start, the idea is to always start with z mod 5, f5, and find an irreducible polynomial of degree 2. Why is that? Why will that do it? Why will that do it? If you find an irreducible polynomial of degree 2, then the quotient ring is a field. We're done with this. Now, why does it have 25 elements? What are the possible remainder when you divide with degree 2? They're of the form a plus bx. Right? How many choices do you have for a? How many choices do you have for b? How many choices in total? How many choices for the remainder when you divide by degree 2 you have? 20? Right? You see that or not? take f of x and divide by and take let's say I don't know x squared plus 2, x squared minus 2. Let's see. Well, let me find an irreducible. Well, take a polynomial of degree 2. Let's say x squared plus 2. 1 plus 2, 2 plus 2. Yeah, it's not 5. Okay, 2 squared plus 2 is not 5, not 0. Okay, great. So take x squared plus 2 and have 5 of x. When you divide by x squared plus 2, what are the possible residues? These are all the linear polynomial, or at most linear polynomials, in f5 of x, right? Now, how many of these you have? How many choices for a you have? You're working in Z mod 5. So what is this one? How many choices? How many choices for this one? How many choices for this one? For B? 5. In total, how many choices? 25 choices. So, yeah.
But how can you be entirely sure there are no duplicates happening?
It's unique because of the uniqueness of the remainder. Right? The remainder is unique. It's unique because of the uniqueness of the remainder. So you mean why can't a number be congruent to both of them? To two linear polynomials, right? But that's unique because the remainder is unique. Okay? So x squared plus 2 in f of 5 of x. Is it? Yes?
Could you explain the relation between a plus, like the a plus bx and x squared plus?
Sure. Take any element in f5 of x and do the Euclidean division by x squared plus 2. What is the remainder? It's of this form. Agree? Right?
Can you explain why?
This is because when you take the remainder of f by x squared plus 2, the degree of the remainder is strictly less than the degree of x squared plus 2. Agree or not? Yeah? Have we seen division of polynomials before? You have seen that the degree of the remainder is strictly less than the degree of the thing you divide by, no? And it's the same thing here. Take f of x and divide it by x squared plus 2. What is the degree of the remainder? What can you say about the remainder?
So it has to be strictly less.
Yes.
A plus bx is the residue.
Is the remainder, the residue. Yeah, you call it residue, remainder, all of them is true. All of them are terminology. So how many choices for the residues you have? If it has coefficient in Z mod 5? 25. Okay? So the idea, if I tell you construct a field with 25 elements, then you start with Z mod 5Z and find an irreducible polynomial of degree 2. If I tell you construct a field with, let's see, 27 elements, what do you do? What do you start with? Please raise your hands. Yeah?
You start with that 3 and you find the polynomial of degree 2.
That is irreducible polynomial of degree 3. Very good. If I tell you I need a field with 16 elements, what do I do? Please raise your hands. Yeah. In? So 2 to the 4. In F? Exactly. If I tell you find a field with 81 elements, what's one way of doing it? What base field do you start with? Yeah?
3.
F3. And what do you need to do?
4 elements of the
No.
so there are 3.
No, so 3 to the 4, 81. So what is the degree of the polynomial?
4.
4. And what must it be? Irreducible.
Oh.
Yeah? Yeah.
But how can we show it's irreducible now that we don't have any more the rule that it has no roots?
Pardon me?
How can we show it's not irreducible once we no longer have the rule?
I'm not saying that the root method will work, but I'm just saying if you can manage to construct one, which is not an easy task in general, then that's how you get it. It's not easy to construct a polynomial of degree 4 that is irreducible in Z2, let's say. Z2 is the simplest case, and it's not easy. You have to do some work. Let's do one more. I need a field with 49 elements. I need a field with 49 elements. How do you start? Construct a field with 49 elements. Yes?
So 7.
Yeah, F7, and then what do you do?
Degree 2.
You find, yeah, degree 2, but an irreducible polynomial of degree 2. Okay, let's one more, it's very important. Let P be a prime congruent to 3 mod 4. P is congruent to 3 mod 4. Okay? We know something from the midterm that x squared plus 1 has no roots in Fp of x if P is congruent to 3 mod 4. Do you remember this question from the midterm?
Yes.
X squared plus 1 has no roots in F3 and Fp of x is P congruent to 3 mod 4. You remember this or not? You agree that if I cannot find an element in Fp such that a squared is minus 1, then x squared plus 1 has no roots. Yeah,
No roots in F4.
in Fp.
Okay.
In Fp, right? Has no roots in Fp. How can you find a polynomial, how can you find a field with p squared elements if p is congruent to 3 mod 4? If p is a prime congruent to 3 mod 4. You just take Fp of x, right? You start with Fp, and an irreducible polynomial of degree 2 is a field with p squared elements if p is congruent to 3 mod 4. So for example, I need a field with 11 squared elements. What do you do? 11 is congruent to 3 mod 4, yeah. What do you do? 11 is a prime congruent 3 mod 4. What's an irreducible polynomial of degree 2 in F11? X squared plus 1. What's an irreducible polynomial of if I tell you construct a field with 103 squared elements? How do you do that? 103 is a prime. Of degree 2. Do you know what it is? Do you know what's an irreducible polynomial of degree 2? This one. X squared plus 1. So if P is congruent to 3 mod 4, x squared plus 1 will be irreducible in Fp of x. Okay? So again, don't be intimidated by number. Let's say in the midterm, I give you a large prime
Midterm.
on the final. If I give you a large prime congruent to 3 mod 4, and I tell you construct a field with p squared elements, try to start like that. Okay? Yeah.
I'm not sure if I understand. Can you explain again why x squared plus 1 is always irreducible in C?
Yeah, if p is congruent to 3 mod 4.
Yeah.
We showed that x squared plus 1 has no roots in Fp, right? In the midterm. You have no element such that a squared is minus 1. This means that x squared plus 1 has no roots.
Why?
If you have no elements that satisfies a squared equal minus x squared equal minus 1, this means that x squared plus 1 is never 0. So what this means that p is congruent to 3 mod 4. And this means that x squared plus 1 is irreducible.
It's irreducible.
It has degree 2 and has no roots. So it's irreducible.
That's quite